All right, good morning. My name is Greg Wadley with CTC and Associates. I'm the Clear Roads Administrator. We're here for the final project webinar for the project entitled Effects of Additives in De-icing Salts at Lower Temperatures. This research effort was led by Laura Fay at the Western Transportation Institute at Montana State University. This webinar is being recorded and will be posted on the Clear Roads website later this week for viewing by you or your colleagues at your convenience. We also ask that unless you're speaking, please remain off camera and keep your microphone on mute. However, if you have any comments or questions, please enter them into the chat box and we'll address them at the end of the presentation. All right, Dr. Fay, I'll turn it over to you.
Thanks, Greg, and thanks for everyone who was able to make this. So I'm going to go into presentation mode, which means I can't see if there's comments. So feel free to either speak up or I'll have Greg maybe notify me if there's something in the chat.
I'll do that.
Thank you. All right, so we are here to present the final report for Clear Roads Project 22-03, which is titled The Effects of Additives in De-icing Salts at Lower Temperatures. I've included the link to the page. I'm sure everyone on here is from Clear Roads, so you know, but again, that's where you can access all of the materials. So as a reminder for everyone, the objectives of this project were to evaluate the impacts of additives mixed with solid rock salt and those impacts that they have on the eutectic temperature. And this was all under the guise of doing laboratory testing. So determine if additives lower the eutectic temperature for each different product combination, if so, by how much. And then also if there's some additive performance benefits that you get from these additives that are added to rock salt. So with that, I'd like to acknowledge the project panel for this. There were quite a few folks that are listed in the report. I'd like to thank Minnesota DOT for being the pool fund coordinator and the project liaison. Greg has been wonderful helping to coordinate the project. We had many survey respondents that were very helpful. And then also specifically, the agencies listed below provided all of the products that were used for testing. So huge thank you to those agencies for providing it. So just a quick overview of, I'm going to do a high level presentation. I'm not going to get into the weeds here, but we're going to talk about all the task work that was done. So initially we performed a literature review that was followed up by a survey. Then we conducted lab testing, and in the report, we also have some recommendations and suggested future work. So some of the major findings from the literature review are presented on the next few slides. And I think we all know, but chloride-based salts are a cost-effective and practical solution for winter maintenance operations. And these chloride-based de-icers and anti-icers can have negative impacts to infrastructure and the environment, which may in part be addressed by the use of additives. So that was some of the impetus behind this project. Specific environments and situations, such as extreme cold, may require the use of additives to effectively treat roadways. So are these additives providing cold temperature modification? Additives are used in many ways to increase de-icer efficiency and effectiveness while improving mobility and safety. And some of these benefits that are known and well documented are corrosion protection, cold temperature modification, and then also anti-caking properties. Other benefits that are known but maybe less quantified are residual effects that may occur, or performance benefits in general, or generally being environmentally friendly. And so those were explored in depth in the literature review. Another piece of the literature review was looking at all of the testing that has gone on rock salt products and then rock salt products that were blended with different additives. And so there's extensive tables of data from each of these different test methods. So we looked at eutectic temperature, calorimetry, measurements of ice melting capacity using the various test methods. And then based on that SHARP test method, there's your ice penetration and ice undercutting test also, road grip and bond strength. And again, in the literature review, there are extensive examples of all the data that's been collected and all the different additives that have been tested. So from that, we kind of came up with a list of agencies that we would like to hear from and questions we'd like to ask them. So we sent out a survey and we got 19, well, actually, we got more response. We got 27 responses, but from that, we identified 19 unique additives or products that already have additives added to them, which was very helpful because this might be a solid product that's purchased with additives already. It might be a solid that you add something to, or it might be a liquid that's already made with an additive, or again, a liquid that you add something to. These agencies noted that they are using additives, number one, for better performance. Number two was cold temperature modification. Number three was longer presence on the pavement, so that residual effect. And then cost effectiveness and reduced corrosion work almost identical in terms of their level of importance for being used. Other benefits that were identified include being able to use less product or reduced application rates, and through that cost savings while still achieving the same level of service. Another person or agency noted that they have clearer roads and faster cleanup, that they see enhanced performance, and that the visibility from the additive in the product makes the drivers have more comfort. And as you know, there are many products that either have whether it's like natural minerals in it, or it might have an additive that's a dye so that you can actually see it when it's out there. We did also ask about some impacts because just like any de-icer, additives can have impacts also. And agencies noted that there were some complaints from the public. They didn't detail what the complaints were or why they were complaining. They did receive complaints about sticky residue, and some of these products, especially the agricultural organic products, they can be very sticky and very viscous. So that's definitely noted. They also received complaints or noted rusting and corrosion issues. And then also another agency noted that with the use of the new additives, they were not able to blend the product anymore. So that was interesting. So we took all the information from the literature review and the survey, and we came up with a list of potential rock salt and additive blends. And we proposed some test methods. And what we landed on was basically what's shown in this matrix for a testing plan. So we landed on 8 different products to be tested. And those were a solid rock salt and a clean one. So we used a lab grade purchased rock salt, a mined rock salt, so ice slicer, and then another commercially available rock salt with an additive, which is ice kicker. The remaining products were all pre-wet solids. So we used our reagent grade rock salt and we pre-wet with salt brine, beet heat, beet juice, MMZ or magic -0, and mag chloride brine. And again, all of these products were not provided by the vendors. They were provided by state agencies as they received them. The only product that was purchased was the reagent grade rock salt. All of the pre-wetting was done at 8 gallons per ton, and that was guidance that was provided and approved by the project panel. So with those products, we did the following testing. We measured freezing point and the solubility limit to determine the eutectic temperature. We used a modified ice melting rocker test. Because we're using solid products, they had to modify the test method for that. That was done at 2 temperatures. And we did a friction analysis where we looked at, as these are applied to the pavement, what happens to the pavement, the friction on the pavement surface. And again, that was done at 2 temperatures as well. So one interesting piece of this with the solid products is we did a gradation analysis. Here you can see a picture of what these products look like. So we have on the left-hand side, we have the purchased or lab grade, reagent grade rock salt. We have ice slicer in the middle, and we have ice kicker. We went in and initially we pulled the gradation analysis provided by the vendors because we were going to use those products as is. We weren't modifying them. But we did want to tailor the gradation of the reagent grade salt to be as close or within range of the commercially available products. What you can see here on this table is the different sieves that were used in the gradation analysis and what was measured. So for the reagent grade rock salt, you have a pretty uniform distribution of large, medium, and small, with note that there's a very small percentage of fines though. With the ice slicer, initially, again, we pulled that from the website, and so there are ranges reported, so that's the fourth column over. But then we measured it after the fact, and this is something we would take back if we could, but this is how it was done. So what we found was that the reported gradation on the website, it does not match necessarily what we actually had in the sample. There was a significantly higher amount of fines in the ice slicer. And again, for the ice kicker, they reported on their website slightly different sieve sizes, but categorically they matched, but again, still a much higher amount of fines than what was in the lab grade product. So getting into the results. So initially, the first test that I'll talk about is freezing point and the solubility limit. And again, that's to try and get at the eutectic temperature. So I'm going to talk through this one figure so that then we can look at all the summary data. But essentially, the freezing point for different concentrations of solutions was measured. So that was a 5%, 10%, 15, and 23% solutions were measured. And when you look at the graph here, you see a blue dotted line that goes on the left-hand side all the way down to meet this dark black line. And that line there is your freezing point line. And then for the solubility limit, that's the point where if you add more product to that solution, it actually crystallizes out. So you're not seeing better performance, you're actually seeing some of that material precipitate out into the solution. That's your solubility limit line. And that starts at that, I guess, red line, that 23% line, and it goes up to the right-hand side. And this gives you what is called your eutectic curve. And at that point where your freezing point line and your solubility line meet, that is your eutectic temperature and your eutectic concentration. So this is how all of these plots were made. They were measured in the lab. And I will now go to the summary data. So all of the estimated eutectic temperatures are provided here for all the different products. What's interesting is that, I guess to note is that all these products are basically just rock salt. They're 98% rock salt. So you would expect all of the eutectic temperatures to be fairly similar, and they are here. What you can see is that the estimated eutectic temperature basically ranged from, and this is in Celsius, but basically from -4 to -7.4. And so that's a very tight range. That's very close. So these additives did not have a huge influence on the eutectic temperature. What's, I guess, different about this is that you'll see that ice slicer has two different temperatures noted here, and I'll explain that on the next slide. So when you are doing the solubility test, you have to physically look and visualize if salt crystals are coming out of solution. And here in the beaker, you can see that the solution with the ice slicer was very murky. It was impossible to tell if crystals were coming out of solution. So for ice slicer, they were only able to determine the freezing curve. And so from that, you'll see that in the report in here, there is only a freezing curve reported. They also did an analysis where they looked at the weight percent of, I guess, the insolubles, which is basically the dirt, the natural products that are in this mine material that are not rock salt, that would not go into solution. And it actually represented a pretty high percentage. It was about 5 to 15% of the total weight. And so when they put this product into solution, what they found was that as is, by application rate, there was a reduced eutectic temperature, or a warmer eutectic temperature is observed here in the upper line of ice slicer, when all of the fines were included. But when you took into account the percent of fines that are not salt, and you actually increased the volume to account for a true 23% salt solution, you actually had to increase that to 26% to get a similar eutectic temperature for ice slicer. So that's the only one that had kind of a unique situation here. So moving on, we also looked at the modified ice melting capacity rocker test. So again, this is a modified version of the rocker test that was to handle solids. Currently, the test method is only validated for liquids. So this alternate test method was developed and used here. But just to reiterate, these results in this test method for solids is not yet validated. So please, you may look and consider these results, but you can't compare them to results from liquids. So here are some of the results for ice melting capacity. And what we have here is that you can see here pre-wet solid with beet juice, so pre-wet solid 2, so sodium chloride pre-wet with beet juice had the highest ice melting capacity. And that overall, most of the pre-wet products had the higher ice melting capacity rates than the commercially available solids, and even than the controls, which was interesting. And so this was done at 15 degrees, and then it was also done at 25 degrees. 25 degrees was the warmest limit on the freezer that was available for this research group. So that's why it was done at that temperature. So again, at the warmer temperature, again, you're going to see higher ice melting capacity rates across the board. But what is interesting is that you still see the sodium chloride with beet juice as the top performer, and all of those pre-wet products, so the rock salt with the additives, performed overall very well in ice melting capacity, with, again, some of the commercial products performing well and on par with or lower controlled products. So in summary, for the ice melting capacity results, again, we see that the pre-wet solid 2, or sodium chloride pre-wet with beet juice, had the highest ice melting capacity at both temperatures, 25 and 15 degrees. But again, a lot of the pre-wet solids performed very well, whereas the commercial products and the control products, so rock salt alone, and then rock salt pre-wet with salt brine, did not perform as well in terms of ice melting capacity with this test. Something to note here is that I mentioned earlier the gradation and the gradation difference between the rock salt control that was used to make all the pre-wet products and the controls, and then the commercially available products. So we did put a caveat in the report that the gradation may have affected the results here. And the gradation note that for ice slicer and ice kicker had substantially more fines than all the other products that were tested. So a little side project that was done to help us understand some of these results was just for the control products. So rock salt and rock salt pre-wet with salt brine. The modified ice melting capacity rocker test was completed with 15 minutes of shaking time and 30 minutes of shaking time, just to see if there was an influence of the shaking time on the results. And basically what you see here is that, yes, the longer the material is allowed to be in the shaker or rock on the table, the more melting you would get, which is what you would hope to see. What is interesting here, though, so we have for the solid control overall performed very well at both temperatures. And you see in most situations, the pre-wet did not outperform the solid control, except in this one scenario that after 30 minutes of shaking, the pre-wet rock salt did have a higher ice melting capacity than all other situations. So that was an interesting finding that pre-wetting alone may not influence ice melting capacity results, which is interesting given the results on the previous slide, which show that overall pre-wet products, so the rock salt pre-wet with these additives, seems to have higher ice melting capacity. So moving into the last test that was completed, again, we conducted a friction testing. So the products were converted into liquids and applied to the pavement surface. And the shear force measured to drag a weight across the pavement, so asphalt and concrete, was measured before any product was put on it, and then over time. And it's interesting here because what you see is at time 0, you see fairly high surface friction, which is great. You see it just above 0.6 all the way up past 1. So good quality pavement friction, safe driving conditions. And then after application of the liquid, you see in most situations at 15 minutes, a significant drop in friction. And so this is that liquid on the pavement, and that friction is reduced because of that liquid. And then we're in a 30-degree cold temperature chamber here. So over time, we're measuring this friction. So it's interesting that at about 30 minutes, 2 clear groups emerge where you have higher friction and you have lower friction or consistently low friction from the 15-minute test. And then after 45 minutes, all of these products either remain level or friction improves for them. And that kind of remains steady throughout the test period. What's interesting is that there's a significant difference between pre-application surface friction and post-test friction, and that the final friction values landed around 0.63, so considered safe by a friction standard. 0.6 is usually considered a safe driving condition. Anything around below that or 0.4, you're going to want to start with winter maintenance operations. So the biggest concern was initially within that first 15 to 30 minutes when the product was applied. Now, we also did the same testing at 15 degrees. And what you see here is another interesting trend where you have a start of surface friction being fairly high. But in this test, it was grouped by pavement type. So the upper values at time 0 for the pavement are asphalt, and the lower friction values at time 0 are concrete. And then as you apply the product, again, friction drops for the asphalt, but for concrete, many of the products remained level. And then after 30 minutes, there was a split again in which products either remained at higher friction values or had a drop in friction. What's interesting is that the products that had high friction at 30 minutes, at 45 minutes had a significant drop in friction, and the opposite was true. The products that had low friction at 30 minutes had an improvement in friction by 45. And then after the hour, almost all the values coalesced around 0.6. So again, a good, reasonable friction value. So I think the big takeaways here are that the pavement type had a significant influence on the results, and that for the different additives that were added, they influence the friction at different times. And so that may have to do specifically with the additive type and the product mixture. And more work would be needed to really tease out what was going on there. But just to further validate the importance of pavement type, what you see here are after 60 minutes, these are all the results for the asphalt samples in orange. So really tight, really consistent results for both 30 and on the right-hand side, 15 degrees Fahrenheit, whereas the values from the concrete samples were much more variable. And so this might speak to the test method. And that's something that could be looked into. If we use a different data source, it may not look the same. But clearly pavement type had an influence on the results here. Oh, sorry. So moving forward into the conclusions, the literature review found an abundance of information on how additives affect the performance of rock salt and salt brine. And they were identified and reported in a number of tables. We also identified well-established test methods in most situations that have been used and reported good and reasonable data. In addition to eutectic temperature or measuring of freezing point, ice melting capacity, calorimetry, ice penetration, ice undercutting, and road grip and bond strength are all test methods that have quite a bit of data published on salt with additives. So, and then there was also a good bit of information on concerns and limitations existing with the current test methods. And we we ran into that with the rocker test not being validated yet for solid products. But this applies to some of the other tests as well. For example, ice penetration and ice undercutting tests also have very high error rates in addition to the other ice melting tests through the SHARP procedure. So from the lab testing, what we can say about the freezing point results or the estimated eutectic temperature is that because they were all basically salt-based products, sodium chloride-based, they had very similar eutectic temperatures. So around -6. And that from this test, rock salt and pre-wet salt with magic -0 mmZ showed the lowest freezing point. But again, when you look at the error or the standard deviation here, it was very minor. These were all within a degree or two of each other in terms of eutectic temperature. What was also interesting when you compare these results to the ice melting is that a lower eutectic temperature for one pre-wet salt over another does not directly correlate to more ice melting. So getting into the modified ice melting rocker test, these are the results from top performer number 1 down to the, I guess, least ice melted. And for both tests, at both 15 and 25 degrees, sodium chloride pre-wet with beet juice had the highest ice melting capacity. But again, most of the pre-wet rock salts with the additives that were identified had the higher ice melting capacity rates, followed by ice kicker, and then the control products, beet heat, the pre-wet control, and then ice slicer. And with the friction results, I think what can be seen is that there was no clear best performer. We couldn't rank one perform better than the other. What we could say is that the addition of de-icers creating liquid on the road reduced friction, which we all know that happens, and that the products each either added value or reduced friction at different times during testing. But after an hour, they all kind of achieved a reasonable friction value. So, but what's interesting to note is that for some of the friction measurements, the values were very consistent over time. So they had the least reduction in friction over time. And so at 30 degrees, that happened to be sodium chloride pre-wet with beet heat and sodium chloride pre-wet with brine. So the pre-wet control. And then at 15 degrees, the most consistent friction or the least reduction in friction over time was associated with ice kicker and sodium chloride pre-wet with MMZ or magic -0. So in terms of recommendations and future research, one thing that became very clear, especially as we dug into the literature, was that it would be really nice if there was a public-facing or managed database of de-icer testing results so that you could very quickly, easily look at, for example, the ice melting rocker test, all the papers that have been published, all the results, and all the different products that they've done testing for, so that you can very quickly see the results and compare your findings to others. One thing that's definitely needed is that the rocker test needs to be worked on to either be validated or standardized in a way so it can be used for solids. A huge portion, if not the majority of de-icer materials that are used are solids. And so we do need a way to test them. And if the rocker test is not the way, then we as a user group and research group need to come up with a better test method to test them. The other piece that I think would be really helpful is to look at the gradation analysis and how gradation affects performance, not only in the field, but also in these different test methods. Specifically, we don't know the level of influence the gradation had on the rocker test in this example. And then also, you know, we used a reasonable pre-wet rate for the field. We used 8 gallons per ton. But for the lab, it would have been nice if we could have also mimicked the bulk of the testing, but at a much higher pre-wet rate to see the influence of that. We definitely would recommend additional testing at higher liquid additive rates. So with that, I will say thank you for your time. I'm going to hop out of presentation mode, and I would take any questions from the group.
All right, so we've got a question from Carl. Carl Fetters from Michigan. It says, will the final report have the background data used to create the friction graphs? I was having a hard time following the different colors.
Yes. So in the Appendix C of the report, we have all the data tables with all the friction data so that you can go in and look. And if folks want, after the fact, you know, we could provide the actual files for you to keep on your member site. So yes, the data's there. But yes, it is hard to track with all the 8 different samples we were testing.
So Clay Adams from Kansas has his hand up.
Good morning or good afternoon. I may have missed it, but on the blends, what percent additive did you use? And was it the same for all of them?
Yeah, I'll go back to the table just so you can see. For all the pre-wet products, we added the pre-wet at 8 gallons per ton, and all of them were the same. So the only unique or different situation were the commercially available solids, where, you know, Ice Picker has a coating and the coating rate we're not sure of. And then Ice Slicer has the insolubles present in it. And again, we measured about 5 to 15% insoluble dirt, rocks, things like that.
Okay. I know this is research, but do we need to use Celsius temperatures? One of the graphs didn't reflect the Fahrenheit, and you know, in other graphs, well, you've got a mix here. Here you're showing Fahrenheit, but one of the graphs was just entirely in Celsius, and I wondered if that could be, if we could be consistent through the report.
Yes, we will do that.
Okay. And then on some of the graphs, the graph label was IMC without a explanation of what IMC was on the graph title. And I guess I'd like to see it spelled out.
Okay. Thank you.
Okay, I don't know if my other question makes, I had the same question about the pavement types on the friction graphs that without having that information on the graph to identify with the swoopy curves, without having, I think it's the next one where you say it's pavement, where it's based on pavement type.
Yep, so it is, blue is labeled as concrete and orange is labeled as asphalt in both. And on the swoopy graphs, after, like, for example, the legend on the right-hand side, it says NaClA in parentheses, that's asphalt, and NaClC would be concrete. Okay. And the distinction in the graph is that the asphalt are all the straight bold lines, and the concrete are all the dashed lines, and that's consistent through both. But
Okay, I didn't notice the C and the A after I guess maybe the print was too small for me to see.
I will also double check that that's well defined with the figures in the report so that that's clear.
Okay, all right, thank you.
Yeah, thank you.
All right.
One
Does
last
anybody else have
question. One last
go ahead,
question, Laura. I got a Beat Heat sales brochure in front of me where they did pre-wetted rock salt ice melting performance comparison at 25 degrees Fahrenheit that was performed by Advanced Laboratories Inc. in Salt Lake City, Utah. And it's based on milliliters of brine created equals ice melted. And I didn't know not you had seen that as part of your literature search.
If we did pull available materials that were on the web from all the product vendors, and we did, the literature is very extensive. I don't know if that's actually considered published material, but Mike, thank you for bringing it to our attention. I'll double check that we have that. I don't know if it could be added to the lit review if it's not there.
All right. Does anybody else have a question or comment for Laura? Jasmine? Oh, yep, comment. Thank you. Okay. All right. Well, we have something in the chat, or is that also Jasmine? Yep. Okay. So, so Laura did provide, and her research team provided the final report recently. So the research team will, or excuse me, the project subcommittee will be going over that and providing their feedback on it. Excuse me. This presentation, as I said before, will be uploaded to both the project page and to the webinars page that we have on our website under resources, videos and webinars, I think it's titled. So that could happen tomorrow, but it's more likely going to be next week. And then I will send out an email notifying everybody of it being up and posted. So with that, since I'm not seeing anything more, I want to thank Laura and her research team for all her hard work on this project. Greatly appreciated. As always, it's a very high quality product. And like I said, once the final report is reviewed and has time and has an opportunity to be formatted, we'll go ahead and get that posted as well. I'll also notify you when that's up. And yeah, so I think that's about it. Appreciate everybody joining today. We had a great attendance, and have a good rest of your day and a good weekend.